Well, I hope everybody got a good shot of caffeine to hear the rest of the talks this morning. I was pleased to hear from Torsten's talk this morning that geology has a relevance to geodynamics because that's what I care about. I'm a geologist. I study metamorphic rocks exhumed from subduction interfaces. So what I'm going to be talking about today is what we can learn about subduction zones by looking at rocks, the metamorphic rocks that are exhumed from the subduction interface. And one of the take-home messages is that subduction zones are very complicated. What we see, the evidence that we see from rocks that are exhumed from subduction zones is that there's a lot of complexity, but we can also learn a lot about the processes that occur within active subduction zones by looking at the rocks that have been exhumed from fossil subduction zones. So I have here, the stereotypical cross-section of a subduction zone. And of course, rocks are exhumed from lots of different parts of subduction zones. For my research, I focus on rocks that are exhumed from the subducted slab. So my talk is going to focus mostly on subducted slab, relatively deep rocks, a little bit of the shallower part of the system as well. And these rocks tell us about a lot of different things. They tell us about the materials that exist within subduction zones. So it's our only direct sampling of these materials that have been, at that subduction interface. So we get information about the mineralogy and the properties of those materials. The conditions, pressures, temperatures, fluids, so forth that are experienced within subduction zones, and then the processes that happen within those subduction zones. And they provide complementary information to observations from active subduction systems. And so this is a diagram of the so-called subduction factory from Tatsumi in 2005. And this is one way to look at a subduction zone, which is you have input material, oceanic input, oceanic crust, sediments in the brown on the top. And then you have outputs, various outputs. You have arc volcanoes, so some people interrogate subduction zones by looking at arc volcanoes. You have earthquakes, another output from a subduction zone, so you can investigate earthquakes, mantle, residue material, and so forth. But what I study is what goes on inside of this subduction factory, right? So all of these inputs go into the subduction zone, into the subduction factory. We can interrogate a variety of outputs, but really what I want to know is what's going on inside the subduction factory. And this is a diagram from a paper that I co-wrote with Gray Bebout. And essentially, I want you to contrast this with the diagram that I showed earlier, and that is that this subduction interface, what we see from the rock record, the subduction interface itself is really a lot more complex than we draw in our simplified two-dimensional diagrams of subduction. And so we spent a lot of time reviewing the literature and looking at different features that are found in exhumed metamorphic rocks. And you can see that we sort of try to encompass all of what is found in metamorphic rocks in this diagram. Now, this is not representative, perhaps, of a single subduction zone, and there's probably some issues of scale in here, but it tries to encompass a lot of the different processes, like fluid flow, you see the blue arrows, mixing of materials, you see the different colors representing different rock types getting mixed at the interface, of course, deformation, faulting, and so forth, veining, fracturing. All of these processes create a very complicated interface between the subducting slab and the overlying mantle wedge. So my talk is broken into 4 parts, 4 different types of information that we can get from metamorphic rocks. The first part is thermal structure, where we can learn about pressure temperature conditions from exhumed metamorphic rocks. The second has to do with fluids. Metamorphism generates fluids. What evidence do we see in the rocks exhumed from subduction zones for those fluids? Rheology and deformation. What kinds of histories do the rocks record about the behavior of the material within the subduction interface? And finally, geochemical cycling. So part of this is just to give you some sense of the types of information that we get from the exhumed metamorphic rocks. But I'm also tasked a little bit with telling you a little bit about those rocks themselves. We're having a tutorial this afternoon where you're going to be looking at rocks, and some of the rocks you're going to be looking at are metamorphic rocks. And I know that we have people with a variety of backgrounds in the audience who may not be as familiar with the minerals and rock types that are exhumed from subduction zones. So part of what I'm going to do also is to tell you a little bit about the names of the rocks and the types of minerals that we find in those rocks, so that for the tutorial this afternoon, you're able to hopefully better identify those minerals and give those rocks names. And then also, if you're going on the field trip with us on Saturday, we will again be looking at exhumed rocks from the Franciscan complex, and so that will hopefully help you out in identifying and characterizing the rocks in the field. So that's my talk has kind of two purposes, one to talk about this information and one to introduce you to the rocks themselves. Okay, so to introduce you to the rocks themselves, we'll talk a little bit about the thermal structure of subduction zones. Christy touched a little bit on things that we call thermobarometry. This is based in equilibrium thermodynamics. And so this is how we estimate pressure temperature conditions from rocks that are exhumed from metamorphic, from the subducting slab. We use equilibrium thermodynamics, all right? And this is based on the fact that systems, chemical systems, tend to minimize this quantity called Gibbs free energy, right? This is a chemical potential energy. And a lot of times in teaching about this, we use this kind of diagram, and the analogy is made to gravitational potential energy, right? So in gravitational potential energy, systems tend to minimize that potential energy, right? If I have a ball here and I let loose of it, it will fall to minimize that gravitational potential energy. So we have a similar kind of concept here with this Gibbs free energy, where high Gibbs free energy is up, and low Gibbs free energy is down, and the system will act to minimize the Gibbs free energy of the minerals that are of the rock, the minerals that are present. And so what's shown here, you can see there's some topography to it, it's not just up and down, right, is carbon. And so carbon, at Earth's surface, the stable form of carbon is graphite. Okay, so we see here stable graphite, that's the minimum Gibbs free energy configuration for carbon on the Earth's surface. Right? We also, however, have diamonds. I have an engagement ring that has a diamond, and it's not turning to graphite anytime soon, okay? We call this metastable, all right? So it actually has a higher Gibbs free energy, but it's got this little activation energy, that's what this E sub A is meant to indicate on here, that it has to overcome in order to convert to graphite, okay? And so this reaction takes place at a very sluggish rate because of this activation energy. And so we have diamond that's stable at the Earth's surface, even though we have diamond at the Earth's surface, even though it's not stable. Okay, but generally speaking, systems act to minimize Gibbs free energy, and that's the basis for all of the estimates of pressure and temperature that you will see in the literature based on mineral assemblages, mineral compositions, and so forth. Okay, how many of you seen this diagram before? Okay, awesome. So I don't spend a lot of time on it. This is a metamorphic facies diagram, okay? And this is based actually originally on field observations of metamorphosed mafic rocks, okay? And so all of the different names in these different fields, so temperature on the x-axis, pressure on the y-axis, these are the names of the metamorphic facies, and they were based on mineral assemblages. So not just a single mineral, but a grouping of minerals that were found in a rock. Right? And the facies, they recognized that different mineral assemblages represented different pressure temperature conditions, and over the years people have started assigning temperatures and pressure conditions to this diagram. What is also on here, in addition to the various facies names, are these arrows. And the arrows represent pressure temperature paths. Okay? And so we can imagine a rock at the Earth's surface, actually off to the left here on the diagram, encountering a variety of tectonic environments and following different paths on this pressure temperature diagram depending on the tectonic environment it experiences. So if you have contact metamorphism or a mid-ocean ridge metamorphism, where you actually don't have a lot of pressure but you have a lot of heat in the system, it will follow a path like this bottom arrow, low pressure over temperature environment. If you have continental collision, you get what's called regional metamorphism, and you follow this intermediate P over T line. And you get rocks from zeolite to prehnite pompelliite to green schist facies to amphibolite facies to granulite facies. Those are the names of the facies that the rocks experience. Subduction zones are what we're interested in, and they follow this high P over T line for subduction zone metamorphism, okay, because we're increasing the pressure before the temperature has a chance to catch up with it. And so we encounter zeolite, prehnite pompelliite, but then in most cases we experience blue schist, boy, I can't talk, blue schist and then eclogite facies. I'll be returning to this diagram a few times just to provide a reference frame for this talk. Okay, so a little bit more detail on how these PT conditions are determined. Again, it's this assumption of chemical equilibrium, and there's sort of two basic approaches to this. One of the approaches is classic thermobarometry, all right? And this is based on minimizing the Gibbs free energy of a chemical reaction among minerals. right? So as a petrologist, we look for minerals in a rock. So if we have a rock, for example, that contains garnet and kyanite and quartz and anorthite, we can write a chemical reaction among those minerals. Right? And we then, if this assumption of chemical equilibrium holds, we can determine what the pressure and temperature conditions are for this assemblage to be stable. And it will depend on the chemical composition of these minerals. And so what you can see on this pressure temperature diagram are a bunch of yellow lines. And each of those yellow lines has a different K value. That's an equilibrium constant. Right? That's determined by the composition of these minerals. Some of these minerals, quartz, that's generally pretty pure quartz. But other minerals like garnet can have impurities, can have different components in it, almandine, spessartine, pyrope, and grossular, which is shown here. And so these K values will vary depending on the compositions of the minerals. So you measure the compositions of the minerals, and that tells you that your rock was in equilibrium along, let's say your equilibrium constant is 0.1. Then it defines a line here of pressure temperature conditions for your rock. That's one way that is used to determine pressure temperature conditions. And then ideally, you have another reaction that is a line that's more vertical. This one is referred to as a barometer because it's relatively horizontal. If you can get a thermometer equilibrium assemblage, that provides a vertical line. You can have two lines that cross. It allows you to determine P and T with some precision. Another method is referred to as pseudo-sections, or some people call them mineral assemblage diagrams, or MADs. And in this, again, it's using that same basic premise of minimizing the Gibbs free energy of a system. But here, essentially, the bulk rock composition is input into a large thermodynamic database. And the database, there's a lot of them. You may have heard of Perplex. You may have heard of Thermocalc, Theriac Domino. There's a whole bunch of these that people use and calculate the mineral assemblages that are present for a given bulk rock composition. All right? And so then what that produces, and I think Christy showed this in her talk too, is a diagram like this that shows the minerals that are stable, the mineral assemblages that are stable at different pressure temperature regions within this diagram. And then it also can produce things like mineral compositions, because many of these are minerals that are solid solutions, so they have a variation in composition and so forth. So caveats, there's a lot of concerns. One has to approach these methods carefully, right? Equilibrium thermodynamics tells us about the minerals that are stable at a given pressure and temperature, but it doesn't tell us about how quickly the system might reach equilibrium. My diamond, for example, that's not very fast, right? If I were to look at this now, it's not going to tell me about the PT conditions where it is right now. It's telling us about its peak pressure temperature conditions, right? And that's the general assumption when we investigate rocks, is that the rock is recording its peak pressure temperature conditions, right? And this is because in general, what we call prograde reactions, metamorphic reactions that are happening as the system is heating up, proceed more rapidly than retrograde reactions, which are reactions that are happening as the rock is being exhumed to the surface, as decreasing temperature. So metamorphic rocks can preserve peak temperature conditions, especially if they are exhumed rapidly. But it's always something that as a petrologist we have to be aware of. We look for evidence in the rock textures to tell us whether or not there has been retrogression. We have to evaluate our minerals and our assemblages and our textures very carefully in order to do this type of pressure temperature evaluation. Okay, so in order to give you some idea about the rocks that you're going to be looking at this afternoon, and that are the processes and the minerals that form in subduction zones, I'm going to start with this parent rock, which is a mid-ocean ridge basalt. All right, so you have here a nice picture of a mid-ocean ridge basalt. And I think our igneous petrologist may tell me a little bit more details in this, but basically we have a rock that has plagioclase, some pyroxenes, and olivine. And I've color-coded the different elements because we'll follow some of those elements through progressive metamorphism. So iron and magnesium are green here, calcium is red, sodium is purple, and aluminum, silicon, oxygen are all black. Okay, so this is our parent rock as a basalt, right? But often, before that basalt even goes into a subduction zone, things happen to it on the ocean floor. And so we often can get some metamorphism that's occurring on the ocean floor, and in particular, many basaltic rocks undergo zeolite facies metamorphism. Okay, so zeolite facies, that name zeolite facies comes from the zeolite mineral group. Here we go. Lots of lovely names of zeolites. Any of these familiar to you guys? You don't need to memorize these. These will not be on the quiz. These actually, you won't even see any of these in the tutorial this afternoon. There's a whole bunch of these. They're minerals that have a lot of open structures, a lot of open channels in their crystallographic structures. They're actually very useful in industry. They're used for things like exchanging for hard water to get cations removed from hard water. But what you can see for these is that the feldspar elements, the sodium and the calcium, the feldspars will often react to these zeolite group minerals. And over on the right here, you can see some elements, and I'm only focusing on major elements here. There's a lot of trace element action that goes on as well. But you can see that this type of seafloor alteration commonly adds water to these rocks, also carbon dioxide, and also in many cases significant amounts of potassium. All right, so all of these zeolites, look at the amount of water that's bound in these mineral structures. We've got a lot of water that's added to these rocks on the ocean floor as they're being metamorphosed before they enter the subduction zone. Okay, so the plagioclase, now we've got some albite. The calcium tends to go into the zeolites more and leaving behind just an albite-rich plagioclase. We get some clays that form from those iron magnesium silicates, some other sheet silicates, kaolinite, illite. Illite is the main potassium-bearing phase in these zeolite facies rocks. And then we will get quartz forming in these rocks and calcite forming in these rocks. Okay, the pressure temperature conditions, this just shows some stability fields for the zeolite minerals, so you can get some sense that they change with increasing temperature, but they're all stable at relatively low grade, low temperature conditions. Okay, so that's the zeolite facies moving upwards and onwards into what's called the prehnite pompelliite facies. All right, so we start developing from those zeolites, we now start developing these minerals, prehnite and pompelliite, and this may happen on the ocean floor as well. It may happen as the rocks enter the subduction zone, right? If you saw from the previous diagram, this facies is encountered by all of these different paths. We still have the albite. We start getting some of the sheet silicates reacting to form chlorite, which is another sheet silicate. So smectite in some cases is converting to chlorite. Some of the iron and magnesium from the smectites is being incorporated into the pompelliite. Again, we have quartz, but look at our carbonate phase here. Now we have a mineral called aragonite. And so what you can see from this diagram, it's got the same zeolites that I had on before, but it also has a line that shows where calcite converts to aragonite. So this is a very pressure-dependent reaction. You can see it's nearly horizontal on a pressure temperature diagram. Okay, and it's isochemical. Calcium carbonate converts to, so it's a polymorph. These minerals are polymorphs of each other.
Can I ask a question?
Please.
Before.
That one.
Yes, this one. It only shows a very small part of that result turns into zeolite.
Yeah.
Right? Mm-hmm. And in the phase diagram, you have zeolite turns into pompelliite, prehnite, and so forth. Mm-hmm. So it's only this part of zeolite turns into that. The remaining part of the rock still is the same, right? It doesn't change.
Not necessarily. So, you know, when ocean floor metamorphism and hydrothermal alteration often does occur in vesicles and cracks because that's where the water goes, right? So that's why in this case we have something like this where we've got zeolites filling in a vesicle. And it may be an incomplete reaction, right? Not all the feldspars are going to be converted to these zeolites. But we may then also have our feldspars reacting to form prehnite and pompelliite as water's continuing to flow through the system.
Okay, my question then is, does the oceanic crust that goes into the subduction zone totally change into zeolite?
No, not necessarily.
Okay.
Not necessarily.
So is a small part or is a large part?
Well, that's an excellent question. I don't think we really know. There are some rocks called greenstones that will be in the tutorial this afternoon where you can actually see some feldspar pseudomorphs if you look at them in thin section, which suggests that the feldspar, at least the shape is still retained. We have some evidence for some retention of some of those minerals, but certainly by the time we get to the blue schist facies, we tend not to see any of those relic minerals. That's maybe not a very satisfying answer, but that's what the rocks are telling us anyway.
Just to clarify, by the time, so we're at these sort of lower pressure and temperature metamorphic facies right now, by the time you get up to the higher pressure and temperatures, we think things have completely changed in essence. But how quickly these reactions or how thoroughly they go through is sort of, under, for further investigation.
This falls under those caveats in that these reaction rates are pretty slow because they're relatively low temperature reactions, so they don't happen very rapidly. So they don't go to completion like that. But as we encounter higher and higher temperatures, then we get much more rapid reaction. Okay, so one interesting thing about the calcite aragonite transition is when we see carbonate in rocks, the reaction from aragonite to calcite, back reacting as rocks rise back to the surface on decompression, this reaction actually proceeds very rapidly. So it doesn't have much of a bump in that activation energy, if you will. So it's actually fairly uncommon to find aragonite preserved in metamorphic rocks because it reverts to calcite fairly readily. If aragonite is found in metamorphic rocks, it tells us that those rocks were exhumed very rapidly. So we know something about the rates of exhumation for those rocks. Okay, so let's move up to blue schist facies rocks, right? And so called because they have a lovely characteristic blue color. Anybody know what mineral causes that blue color in blue schists? Glaucophane, yes, excellent. So this is a thin section photomicrograph of a blue schist, and so the blue mineral, blue to purple mineral, and that is glaucophane. Anybody know what these sort of big blobs might be? They're garnet with tons of inclusions, so you see all the brownish looking crap in them. So those garnets have grown other mineral phases, all right? So yes, this is a blue schist, it's a garnet bearing blue schist. So the mineral that gives blue schist its characteristic blue color is a blue amphibole that contains a significant amount of sodium. The end member of that sodic amphibole composition is called glaucophane. Not all blue schists have pure glaucophane, there's a range of compositions. Okay, so some more photomicrographs. And again, this is sort of focusing towards thinking about the rocks that you're going to be looking at this afternoon. Okay, so we've got the glaucophane in both the bottom right photomicrographs. Again, that blue mineral. It's an amphibole. It has sort of an elongate characteristic to it. Garnets, you can find garnet in blue schist facies rocks. And I have a garnet-bearing rock up in the upper right. So you can see this is a relative, well, it's a little bit hard to tell, but it is a blue rock, and it has sort of little brownish spots on it. Those are the garnets. In some blue schist facies rocks, a calcium-bearing phase is actually epidote, which you can see is this sort of really pale green color in the photomicrograph. Anybody know what that mineral is that the arrow points to? It's a long, colorless mineral in photomicrograph. It's a high-pressure form of muscovite called phengite. So you can actually get magnesium-bearing muscovite, referred to as phengite, in high-grade metamorphic rocks. So yes, very good. And then we can also get, that one's going to be hard to tell, that's actually calcite, right? So it's calcite on the surface now, and so I've identified it as calcite, but it was probably aragonite when it was under high pressure. Okay, how about these in the upper left? This is a hand sample photo. Anybody have any guesses as to what those sort of rhomb-shaped minerals might be? Lawsonite, excellent, okay. So lawsonite is another mineral. So these minerals, glaucophane, lawsonite, these minerals are, we can refer to them as index minerals. When we see these minerals are diagnostic of high pressure rocks. These minerals form in these high pressure, low temperature environments. So they're really useful to us in identifying subduction related metamorphic rocks. Okay, here's a longer list of minerals that we find. And again, you can see what's happening with the various components, the iron and magnesium, which minerals are containing the iron and magnesium, sodium going into glaucophane, but also we can, in these blue schist facies rocks, start getting jadeite, which is the mineral formula that's shown here. That's the pure sodium end member pyroxene. And omphacite, where you start getting iron and magnesium and calcium in that mineral structure as well. Here's the phengite, the muscovite that has some magnesium in it, epidote, and I just tried to grab, you may see some epidote in the lab this afternoon, so I wanted to at least show you a picture of epidote so you had some sense for its distinctive sort of pale pistachio green color.
Sarah.
Yeah, Jeff.
It's a geophysicist question.
Mm-hmm.
So in the zeolite phase, maybe you could say that, mineral 1 goes to mineral 5 and mineral 2 goes to mineral 7, but you can more or less, there's some exchange of ions between things, but you started out, by the time this blue schist, it's sort of everything's kind of gone through some chemical blender, more or less, and there's been so much transfer of things from one crystal to another that it's totally presumably totally recrystallized. Is that intermediate phase, where is that? I mean, at what point does this mineral transforms into that mineral stop being a useful way of even thinking about this versus just wholesale transfer of ions?
Well, I think there's kind of two ways to answer your question. One is in terms of physical, like can we see replacement textures, right? Because in some metamorphic rocks, we can actually see replacement textures where one mineral reacts to another. And we can see those at a range of pressures and temperatures. So we can see that up through eclogite facies. Another, though, is to think about the chemical constituents and where they are and the sequences of reactions. And the sequences of reactions can be useful through eclogite facies. It gets a bit more complicated when we have elements like iron and magnesium where we have a continuous reaction. So we can actually have changes in composition of these minerals with increasing pressure temperature, but we don't have an appearance or disappearance of a mineral. I don't know if that fully answers your question, but. Okay, so just some phase diagrams to show you these minerals that I suggested are diagnostic of high pressure temperature systems. Lawsonite, you can see here this red line, so lawsonite's stable above and to the left of this red line. These are actually, this is from a very old study by Louis Liu in 1987, experimental study on mid-ocean ridge basalt composition and the stability field for lawsonite in those particular rocks. And you can see the mineral formula for lawsonite is shown up there. Glaucophane also. And then jadeite. Jadeite is another mineral that we find under these high pressure, low temperature conditions. And the classic reaction is albite goes to jadeite plus quartz. And you can see that reaction shown here by the green line. So the existence of all of these minerals tells us something about subduction zone environments. They're cooler than other settings. I mean, I showed you that on the facies diagram, right? But here we actually have those specific minerals telling us that this subduction geothermal gradient, when we have those minerals, this is a steeper gradient, right? It's colder than, say, continental collision, for example. And you'll see even more detailed facies diagrams than the one I showed you. So this one, for example, which has LBS and EBS separating out lawsonite blue schist from epidote blue schist. And if you actually look back at the mineral formulas, you'll see also that the lawsonite has more hydrogen, more water in its mineral formula. So one general thing that's helpful to keep in mind is that usually minerals that have more water in their structure are stable at lower temperatures. The minerals will dehydrate with increasing temperature, and so we have less water in the structure at higher temperatures. So you'll see diagrams like this. So lawsonite blue schist is stable at lower temperatures compared to an epidote blue schist, for example. So you'll see various diagrams depending on the geologic setting, the compositions of the rocks, and so forth. Okay, I am diverting from that lovely subduction zone metamorphism path to head over to amphibolite for a minute. And I'll tell you why in just a second. But we do find amphibolite facies rocks in some subduction zones. These are some field photos of an amphibolite. And so amphibolites are found in some subduction complexes. That amphibolite facies, that's higher temperature than our classic subduction geotherm, right? So they tell us something about a process, some type of high temperature process that may have happened in the environment where we find it. For example, in some places when amphibolite is found, it's interpreted as representing initiation of subduction. When the slab is first hitting hot mantle, it's a much higher temperature environment than over time when we reach steady state subduction and the mantle has had time to sort of cool down the the slab has had time to cool down the surrounding mantle. So when we find amphibolites, and you can see here there's the reddish mineral here is garnet, so it's not uncommon to find garnet in these amphibolites. The blackish mineral is another form of amphibole called hornblende. But when we find amphibolites, it tells us that there's probably something, maybe subduction initiation, maybe slab rollback, some other process that has created higher temperature conditions than we typically associate with subduction. And one of the reasons I'm putting this in here, other than to tell you that it occurs in subduction complexes, is in the field trip on Saturday, we're going to actually see there are some examples of amphibolites in the locality that we're going to. Okay, so back onto our subduction geothermal. We can get back into our zone of comfort here and go to the eclogite facies. And one comment I have to make is that that you'll see some of the rocks this afternoon. I think these are some of the most beautiful rocks. Who would not want to work with blue rocks, Lucius facies rocks, green rocks? That's what the eclogites are, right? They're these beautiful Christmas rocks. You've got lovely green pyroxenes, and I'm giving away the minerals already, and lovely red garnets. I mean, they're gorgeous rocks. Who wouldn't want to work with such attractive rocks? Okay, so eclogite, so I've already given away these minerals. The mineral assemblage that defines an eclogite is garnet and this pyroxene that's amphissitic, so it has some sodium in it. And so you can see here, this is a photomicrograph. The green is the pyroxene, and then these colorless minerals here are the garnets. And of course, it's not just that. There are other minerals that are found in eclogites. And I should have mentioned this at the beginning. The mineral assemblages that I'm tracing through are the mid-ocean ridge basalt assumption as a protolith, but you can, of course, have metasedimentary rocks that get subducted to all of these different facies. You'll get different minerals that will develop in rocks of different compositions. So eclogite facies minerals, garnet, and again, we've got variability in the composition of the garnet, depending on how much calcium, magnesium, or iron there is. This amphissite pyroxene before jadeite, that's the sodium end member, but we can also have calcium exchanging with sodium, iron and magnesium, making it a little bit more complicated. That mineral phengite, again, if we still have some water, we can have phengite in the rocks. Glaucophane can persist into the eclogite facies. Lawsonite, there are lawsonite eclogites. Lawsonite persists even though there's some water in there. But again, lawsonite eclogites are generally lower temperature than other types of eclogites. We can have epidote and or zoisite in eclogite facies rocks. Quartz, in some cases kyanite, and then again aragonite. And this just shows some stability information for the garnet and amphissite. This is from Schmidt and Poli. Again, this is experimental work on mid-ocean ridge basalt compositions. So you can see the stability fields for amphissite above the green line and for the garnet above the red line for mid-ocean ridge basalt bulk compositions. Right? And so again, if we put our little geothermal gradient arrows on here, these are telling us that the rocks are cooler in subduction zones than they are in other tectonic environments. So we've got, again, our cooler high P over T arrow. Okay, so this begs the question, how cold are subduction zones? And so one thing that I did a couple years ago is to compile PT estimates from metamorphic rocks around the world. So you can see here a map that shows the global compilation. So these are rocks exhumed from subduction zones from around the world. We've got some here nearby. Our Tiburon locality is included in there. Europe, Asia, South America, some Alaskan rocks. We compiled pressure temperature estimates from all of these rocks. But we selected. We did this carefully. We chose the temperature at the peak pressure of exhumed eclogites and blue schist. So what we're going for is the prograde path. All of these rocks have been brought back to the surface, right? So they've all been retrograded, and we wanted to avoid any increase in temperature that might happen during that retrogression. So in all of the studies that we examined, we were careful to filter only the temperatures that were at the peak pressure of metamorphism. And we used only studies more recent than, or since the 1990s to take advantage of the latest advances in thermobarometry. And subduction systems that are less than 750 million years old to avoid the effects of early Earth, hotter mantle and so forth. The distribution of samples from all of these different localities has hopefully given us a wide range of subduction conditions, all ages of oceanic crust, fast and slow convergence, and different ranges of angles of subduction. And so what you see on this slide then is a compilation of all of those rocks. So the colors here are color-coded to the map, and if you want more details, you can look at our paper in Earth and Planetary Science Letters. But you can see there's a range of PT conditions. We have a range of different types of subduction zones. All of these different diamonds then indicate those PT estimates from those different locations. And then you can see we've compiled, this is our average, and then it's a 2 sigma deviation indicated by that blue envelope. And so another thing that we did, though, to make sure that we were avoiding the effects of retrogression is that some of these paths actually compiled PT paths. So they were able to do things like look at inclusions in garnets to get an estimate of, you know, an earlier pressure temperature and a later pressure temperature condition to give us a path. And so what you see are a bunch of arrows that are those prograde paths from a number, we just sort of culled from the studies. Not all of them had these kinds of paths, but to give us some confidence that these are not actually just retrograde products, that we actually have paths, and these paths are consistent with this overall average as well. Yes?
Why is there this forbidden zone?
Yes, okay, so the famous forbidden zone. So that guy Louis Liu that I showed you the diagram from before, he named this the forbidden zone in a paper. It's also in many textbooks, you'll see it as not realized on planet Earth. Essentially, we don't see any rocks on Earth that record conditions that fall on a geotherm that's less than 5 degrees C per kilometer, exhumed from subduction zones.
I didn't see it.
We don't have any that anyone has observed. I mean, you can see from our, whoops. We get close here, but yeah. Torsten.
How many of these are with active subduction zones, and for that subset, do you get any relation with the thermal parameter or anything like that?
So not very many of these are exhumed from subduction zones that are active. I think we've got one over here that's from Cascadia, the Olympic blue schists. But you know, part of our problem is that all of these are ancient, and so trying to correlate it with the modern thermal parameter presents some challenges. So we haven't tried to do that, but we don't have that many that are from active subduction zone systems.
I guess turned around, if you look at the Cenozoic, we have some idea of the inferred plane age.
Yeah.
Is it even meaningful, or are they all much older?
So I have, in that paper, we evaluate this to some extent. I personally don't have a good estimate, but there's a paper by Philippe Agard where he estimates plate ages, plate velocities, and so forth. And we don't, let's see if I can answer your question well. We don't see any preferential exhumation of I can't do this very well on the fly, sorry, of rocks that are young plates that are moving slowly. So we don't see a preferential exhumation of rocks that should be hot, I guess is my sort of semi-answer to your question. And I'd be happy to talk with you more about it after I talk about this, yeah.
Thank you. I'm still a little bit confused about the different colors. Somehow they represent settings or geographic regions?
Yeah, so those colors correlate with this map. So the purples correspond to the North America and South America, the west coast of those continents. The blues are over here in Northern Europe. The greens are the Alps. The reds are Turkey, Greece, and Iran. The yellows are continental Asia, and the purples are Japan and down on to Indonesia.
Right, but is it tectonic setting or is it geography?
It's geography, yeah.
It's geography.
It's geography.
But like the blue are caledonites, presumably.
Yeah, well, okay, so we did do some extent. These are actually sort of, we call them circumatlantic is what we called them.
Okay,
So,
thank you.
yeah. I think, Torsten, in a further answer to your question, using that paper by Philippe and others, there were not very many subduction zones where both the plate velocity and the age of the plate was well constrained. And so we actually only had one that gave us, and we had to bin them into sort of old and cold and young and hot. And we only had one that represented, I think it was young and hot, and a bunch. So it was really hard to sort of tease out any information about that from the data that we had. Matt?
So is that your previous map?
Does that include UHP terrains?
Yeah, it does. So you see we have some, UHP ultra high pressure that's 2.5 gigapascals or higher. So it does include some UHP rocks, yes. So we've got, we've got Norway in there, like the Norwegian rocks.
Is it worth mentioning that the rocks that we have available to us are the ones that happen to come back up again to the surface, and maybe we don't know why some do, and
Sure.
most keep going down. So maybe we're biasing the data set somehow?
Yeah, I mean, these are all, I mean, we have what we have to work with, right? We've only got stuff that's been returned to the surface to work with. So yeah, I mean, potentially, there's a bias. We've thought about different methods of exhumation and whether they might bias that record. And, there's a lot of different ways that rocks can be exhumed. It's just change in geodynamic setting, for example, collision. Serpentinite diapirs bringing things up. And I think in most cases, they won't affect the prograde path. At least that's our interpretation of it, is that they might affect, what's happening on the way up, the exhumation PT conditions, but not so much the prograde path. And that's why actually I think this is particularly important, is evaluating these prograde paths.
We have another question.
A quick question about the method. So here you've compiled all blue schist and eclogite facies rocks, but we just said in a couple slides previous that amphibolite facies could also be recording subduction. Yeah. So would that pull down into the hotter temperature regime there?
Yes, it would. And we tried to avoid amphibolite facies, but you see there's a few rocks here that, they were labeled as blue schist and eclogites. So there's a few rocks here that kind of fall outside. This is a blue schist and eclogite stability field here.
So if you included that, a subduction zone could be significantly hotter than what you're showing on this diagram.
Yeah.
What are the signatures of retrograde metamorphism, and how did you pick that out from your data?
Well, so we relied on the studies, right? And so we were looking for their estimation of what the temperature was at the peak pressure. Okay, so in that case, trying to avoid retrogression. Now, if that peak pressure that happens to be recorded is on the retrogressive path, then there's not much we could have done about that. But in most cases, increasing pressure first, right, and retrogression actually, then the temperature kind of catches up with it. So in most cases, I think that assumption holds.
Is there a certain time scale for exhumation? For example, for certain places, is this something you can use radiogenic dating to constrain?
So that's something I don't know a lot about. Philippe Agard has investigated exhumation rates, and I think broadly speaking, they tend to be on the order of plate velocities, but that's about as much as I know about it. But he's got at least one paper where he talks about that, and I'm happy to help you find that reference if you like. Okay, wow, I'm getting through very slowly anyway. Okay, so we'll leave the thermal structure for a little while and talk about another aspect that we learn about metamorphic rocks, and that is fluids, right? So fluids are really important in subduction zones. This is actually, it turns out, a rather poor resolution reproduction of Horst Marschall's cross-section of a subduction zone, and it's basically to show that, in most of these cross-sections, we have these little arrows that come off the subducting slab that are meant to represent water primarily, but other volatiles that are coming off during all of these dehydration reactions that we have heard about. And so water is important. It is released during prograde metamorphism, and we can even see that when we look at the different mineral assemblages that are stable in the different metamorphic facies, going from our zeolite facies minerals, which had tons of water bound up in their mineral structures, to our blue schist facies index minerals, still some water, but not as much. And then our minerals that are diagnostic of eclogite facies and hydrous. Now I mentioned that we do have some hydrous minerals in eclogite facies, but we're losing water as we go through prograde metamorphism. When we look in metamorphic rocks, what evidence do we have for these fluids, right? So we know that we lose the fluids, but do we see evidence for fluids moving around within these rocks? And so one piece of information that we can find is by looking at veins. And one has to evaluate veins carefully, because you can have closed system veins where you just open a fracture and fluids can actually move from, dissolved material from the surrounding rock can move into that fracture. But in many cases, we see evidence for large scale vein fracturing and fluid flow and deposition of minerals at high pressures that tells us that fluids are moving around at high pressure conditions. Another piece of evidence that we see for fluids traveling through subduction-related metamorphic rocks are found, they're referred to as reaction zones or reaction rinds. And these are features that we see commonly in some of these subduction-related metamorphic rocks, and hopefully if we look closely enough when we're at the field stop on Saturday, and also if you look closely enough in the tutorial, you'll see an example of some of these reaction rinds. You can see one here. I haven't talked yet about melange, but essentially we have these exposures of rocks that are common in exhumed metamorphic complexes where we have these blocks and we have these rinds. You can see here this sort of greenish colored material that's plastered on like a lemon rind around this block. And it's composed of different minerals. It has a different chemistry from the block itself. And these rinds, you can see a close-up rind, and it's actually foliated. You can see this arrow is meant to try to help you see that foliation. Right, so that tells you something about the dynamic nature of the environment in which this rind is forming. But the rinds are commonly composed of minerals that are very hydrous. So this shows a thin section photomicrograph of the block itself. On the left, this is actually an eclogite. And here's a rind, a thin section photomicrograph of one of these reaction rinds. And we can see that there's a lot of hydrous minerals. There's amphibole, there's this phengite, there's chlorite, there's talc. All these minerals contain a lot of water, whereas when we look over at our eclogite, we have dominantly garnet and CPX, which again are anhydrous. We have a little bit of blue amphibole floating around there, a little bit of epidote, a little bit of chlorite. But the rinds themselves are far more hydrous, so they are taken as evidence for fluid interacting with the outer parts of these rinds. And so we can use this kind of textural evidence to try to interpret, and we can use it in conjunction with mineral textures, changes in chemistry and so forth, to try to understand when this kind of fluid rock interaction happens in the subduction environment. And the ones that I've studied, we see that actually this fluid rock interaction that creates some of these rinds anyway occurs a little bit sort of late stage in the history of the rock. So, we've got this 1, 2, 3, 4, and you see the 4 is a slightly, sort of on its way back up. There's also been a lot of studies looking at metamorphic rocks and looking at isotopic evidence for fluid flow. So I show here some results from the Catalina schist, which is another California exposure of subduction-related metamorphic rocks. It's a study by Gray Bebout and Mark Barton in 1989, and they measured the oxygen isotopic composition of these rocks. And what they found at a variety of metamorphic facies. So here's a geologic map of Santa Catalina Island. The blue is the low-grade blue schist and lawsonite albite facies, and then we get higher grade going up to the sort of pink and black. We actually have amphibolite facies rocks on Catalina. And they analyzed the oxygen isotopic compositions of minerals in all of these different metamorphic facies, and they found that they overlapped with the exception of some less altered rocks and some metasedimentary rocks. They calculated the water composition and found that its delta O18 had a relatively narrow range, except for rocks, as I mentioned, that are either unaltered or are sedimentary rocks. And they interpreted that these values, these relatively homogeneous values, were imparted by fluid flow. And so you've got this little sketch over here on the right. These are blocks in these melange materials, melange matrix, and you can see these arrows represent the fluid flow interacting with the outer parts of the blocks, with the melange matrix. Not a whole lot happening in the sedimentary rocks as well. So you can use isotopic evidence like this to try to understand flow regimes, where fluids are flowing, where they may not be flowing, to try to understand how fluids are moving through metamorphic rocks. There have been people who have investigated fluid release rates. And so I show here some results from Bezim Dragovic and others in 2012 and 2015. And they essentially are taking garnets. You can see they micro drill these garnets, right? So garnets, they start growing in the center, and they, over time they grow. And so the center part of the garnet will tell you about the early history of the garnet, and the outer part of the garnet will tell you about the later history of the garnet. So they do these micro drilling, they do chemical maps, they determine the pressure temperature conditions of the inner part of the garnet, which you can see here, the core of the garnet, and the rim of the garnet, so you can get a sense for the changing PT conditions that the garnet has experienced. But then they can also, in these rocks, construct the garnet forming reaction, which you can see in all its glory, all its gory detail down here at the bottom. But the reason to do that is you can actually figure out how much water is released by this garnet forming reaction. Okay, so we've got 0.69, moles of water formed for every mole of garnet. And so then for the bulk rock, you can calculate the weight % of water that's lost during this garnet growth. Right? So in this case, for this garnet, 0.3 to 0.4 weight % water loss during this garnet growth. And then they do samarium neodymium geochronology on each of these different zones. So they take it, they dissolve it, They determined the samarium neodymium age of the center of the garnet and the rim of the garnet. And they've determined that this garnet grew in less than 1 million years. Now, that may sound like a long time to seismologists and people who deal with, sort of short timescale processes, but for a geologist, this is really fast. And really, they're pushing the limits of the measurement. This 1 million years, they can't really do it more precisely than that. So you see it's less than 1 million years. We don't know exactly how much less than 1 million year it is. So we've got a really short time frame. We can quantify the amount of fluid that's released in this time frame. So it gives us some idea of the fluid release rates. And this is one of the areas in studying metamorphic rocks that really is a forefront. People are trying to determine rates and durations of events now. Question?
The samarium, is that based on seawater compositions?
No, so we're looking at the decay of samarium to neodymium and the isotopic ratios within the garnet and the matrix.
So it's actually just general radiogenic decay.
Exactly. It's just straightforward radiogenic decay. Mm-hmm. So this is, another question.
Does that give you some kind of time estimate of how fast this was subducting?
It can, yes, because you have some idea of pressure changes. But again, like I mentioned, right, you've got the time scale is only, it can produce an upper constraint on the amount of time, right? So it's not a precise estimate, but yes, is a short answer. But with a lot of error bars, I think, on that. Okay, also related to fluids, so that's a rate of fluid release. We can look at fluid-related features, so we can look in the rocks for evidence of fluid reactions with the rock, and we can try to get evidence for the duration of fluid infiltration through the rock. And so what I show here is an example of that from the field locality, the Tiburon Peninsula, part of the Franciscan complex. And I have a rock sample from there that's eclogite on the left side and blue schist on the right side. And you see this is, here's a penny for scale. This is a very small scale eclogite blue schist pair, if you will. And what we did was we looked at the minerals in both the eclogite and the blue schist of this rock. And so you've got here some SEM images, backscattered electron images. And what I want you to see is that on the left here, this is the eclogite. And so the O is omphacite, relatively pristine looking omphacite. It's all the same color, right? We also have a little bit of epidote. There's no garnet in this particular image, but there is garnet in this rock. We have minerals that look relatively uniform in composition on the left-hand side of this diagram. This is in the eclogite part of the sample, all right? When we look at the blue schist part of the sample, this is what it looks like. And if you compare this right image to this left image, they're obviously not exactly the same part of the rock, but you can see there's omphacite, but you see how mottled it looks? It's really unhappy. It has altered, okay? And it's altered. The minerals that we can put our electron beam on these minerals, we see diopside, we see pompelliite, we see lower temperature minerals that are present that are essentially this omphacite is reacting away. We also see in this blue schist, we see on the left-hand side, you may be able to pick out the presence of the garnets. It's not the best sample, I realize that, but there are pristine garnets in the eclogite half. When we look at the blue schist half, you can see this lovely hexagonal shape here, but there's no garnet left. This garnet has reacted, you see CHL, it's all reacted to chlorite, okay? Chlorite is a hydrous mineral. Garnet's an anhydrous mineral. So we had some fluid that interacted with this rock. The rock was entirely eclogite originally, but the water reacted with the garnet to create chlorite. It reacted with the omphacite and made it kind of unhappy and created pompelliite and diopside. So we've got petrographic evidence that this right-hand side of the rock was like the left-hand side, but has interacted with fluid and has changed its mineralogy. And so what we did was we took slices along this traverse, just a few millimeters thick. We had a very small saw and cut little slices, crushed it up, digested them, and analyzed for their lithium composition and their isotopic. Yes?
Why do you call the two rocks on the left and the right side blue schist?
So they're the same rock. Sorry, they're different images from the same rock.
Why they're called blue schist?
Because they have glaucophane in them.
Glaucophane?
Yeah, they have a lot of the sodic amphibole.
You didn't indicate.
Sorry, the A is amphibole.
Oh.
So both of these have amphibole. Sorry, I don't have all of the legend on here. I apologize for that. Both of them have amphibole, but there's a lot more of that sodic amphibole in this right-hand sample. It doesn't have garnet anymore. It has very unstable looking omphacite.
If you don't have garnet, can you call it a blue schist?
Yes. Yes, blue schist does not require garnet. It's one of the minerals that can be present in blue schist, but it does not require it. But I can't call this right half eclogite because it doesn't have garnet anymore, and it doesn't have a lot of stable-looking pyroxene.
It's part of the range, right, that's around the eclogite block.
In this case, it's just a pair of layers that are near each other. But the idea is the same, that we have fluid interacting with the eclogite and altering it to this blue schist. And what we did was to measure lithium isotopes across this traverse. Lithium is a fluid mobile element, and what we see is that there's variations in the lithium, so the eclogite's on the left, the blue schist's on the right. We see that the lithium is actually being stripped away. We have lower lithium concentrations in the blue schist than we do in the eclogite. And we see that there's a variation in lithium isotopic composition. So whatever the fluid is that's moving through this rock, it has a higher delta-7 lithium, a higher lithium isotope ratio than the eclogite does. And what we see right at that contact is this little diffusional profile. So Torsten introduced us to thermal diffusivity earlier. We can use mass transport in exactly the same equation, except we have concentration instead of temperature, and we have diffusivity of lithium instead of thermal diffusivity. But it's exactly the same equation, and we can solve this equation, and we get a square root of dt, not kt in this case, for that solution. And so we can determine a t, right? If this were a long event, we would expect a really broad diffusion profile. A short event, we get a very small diffusion profile. We have a very small diffusion profile here. It's half a centimeter or so. So that square root dt is a smallish number. We don't have a lot of constraints on the diffusivity of lithium, but we have some. And so we can estimate the duration of this fluid flow based on this profile. Now there's a couple things I should tell you. First of all, that this is diffusion of lithium within this aqueous fluid, okay? So this blue schist, we're assuming that the fluid is traveling through the blue schist, but it's not traveling through the eclogite, but we have this little diffusive profile of the lithium diffusing through a fluid around the grain boundaries. Okay, so we have to take into account porosity when we're thinking about this kind of estimate. We have to take into account partitioning between the minerals and the fluid. We have to take into account a lot of factors. But we can at least constrain, because of the short distance of this profile, that the duration of the fluid infiltration is likely less than about 100 years, which, you know, I said 1 million years was short before, right? 100 years is extremely short in terms of geologic timescales.
What depth was this rock at? What depth was the rock at?
What depth was the rock at? So this is during, this is a retrograde effect. So blue schist facies, we don't have specific constraints on it, but it was probably somewhere in the neighborhood of 30 kilometers-ish, I would guess.
So it's potentially cytogenic zone depth.
Potentially, yes. Yes.
So most of the diagrams of a subduction zone, like the basaltic crust that we see, we draw a nice little line that says, okay, past this point, we're eclogite, where the slab's eclogitized. But if intermediate depth earthquakes are driven by dehydration, would that be enough to push these things into the blue schist facies? I guess my question is this fluid, is this a temperature effect? Or what's it do to the PT pad?
Yeah, that's a very complicated question, and I will show you another piece of slide here just to show you. This is originally a blue schist host rock, and essentially there was a vein that went through here, and it eclogitized the blue schist. So reaction rates can be enhanced by fluids traveling through the rocks. And so in this case, this blue schist facies rock was sitting around, and it wasn't reacting to eclogite until this burst of fluid came through, and it changed to eclogite. So we can have some kinetic effects due to fluids. I guess that's maybe my short answer, short attempt at trying to answer your question.
Question?
Yeah.
The previous slides, you have this very fast transition from eclogite back to blue schist. This is very interesting. On the other hand, earlier you mentioned that the retrograde metamorphism is very slow. And when you say it was very slow, the impression was that it's much longer than 100 years.
Okay, sure, and that's fair. But again, we have fluids involved here, and so fluids tend to speed things up. And also, this blue schist has not reached equilibrium, so it's not completely reacted. So it is slow in that, you know, the omphacite is still there. It's just really unhappy. So we haven't completely reached equilibrium here.
Yeah, but we see a diamond on your finger, right? It takes millions of years to react back. And we also see a lot of eclogite on the surface, blocks that has been up on the surface for tens of million years.
Sure, and we're relying on this to figure out what those PT estimates are. So,
but if it reacts so fast, I'm not questioning this, okay? I'm just saying it's very interesting.
Yeah. Well, and again, this is a very small part of this rock, right? So we had a very, some fluid that traveled through this rock and interacted with this very small part of this rock. And just to show you that it's not my study that's the only one that has done this type of analysis, so that this is another, this is actually a vein. And so we've got this vein with pyroxene and other eclogite facies minerals in it and surrounding it. And so they also did a traverse where they measured lithium composition and isotopic composition away from that vein and made interpretations on this profile. You see their distance actually that the alteration occurred is much greater. I mean, we're talking about fractions of meters, not centimeters here. And so their duration of fluid infiltration is a little bit higher because it's longer. And they also did some things like vary the porosity and so forth in their calculations. So they did a little bit more sophisticated analysis of these kinds of profiles. But this is the kind of thing that people are just starting to do to try to get estimates of the duration of things like fluid infiltration events in metamorphic rocks. Okay, so some other things, I won't talk a lot about fluid inclusions, but one way to try to understand fluids in metamorphic rocks is to look at inclusions of fluids that are in, bits of fluid that are incorporated into minerals. There have only been a few studies that I'm aware of that have done this, and in some cases they've found very dilute aqueous fluid inclusions. This is from rocks, actually Franciscan complex rocks and some other rocks in the Dominican Republic, and they found relatively homogeneous fluid inclusions in composition and interpreted that to be a flushing fluid of uniform composition interacting with the rocks. And that's contrasted with another study in the Alps where they found very highly variable fluid compositions within a small area, and in that case it was interpreted that the fluid was locally produced by breakdown reactions, and so each little fluid inclusion was recording whatever the minerals around it breaking down had in terms of their salinities. One other sort of interesting development has been the discovery of microdiamonds as inclusions or as parts of fluid inclusions. And so aqueous fluid that contains dissolved carbonate, dissolved silica, and solid microdiamonds actually suggests that carbonate dissolution may be responsible for carbon release during subduction. And so you can see here some pictures of the microdiamonds. Little red arrows here show some of the microdiamonds, and then just the fluid inclusions that host some of these microdiamonds in this study by Frazzati and others. So there's some interesting stuff as we get sort of higher and higher precision and an ability to see smaller and smaller things and look for these small scale things to find evidence for different fluid compositions. Okay. I'm going to touch a little bit on what we can learn about rheology and deformation. I think you're going to hear a little bit later in this workshop from other people on this topic. But it's something that I'm also interested in, and that is what is the nature of the materials that are found at the subduction interface. And we have we draw these nice subduction interfaces as straight lines, but what's really happening at that interface? Do rocks on the subducting plate subduct as relatively coherent sequences of lithosphere? In some subduction-related metamorphic rocks, we do see relatively coherent sequences. Here we see a cross-section from the Italian Alps, the locality called Monviso. We've got some nice serpentinites at the bottom, some metagabbros, some metabasalts, separated by shear zones. But you could think maybe this would be parts of oceanic lithosphere. So we do find places where we get exhumed, nice, coherent sections. We find other locations, however, which we call melange zones. Sorry, I meant to put all these up at the same time. And I sort of referred to this earlier, and this is where we see blocks floating around in a finer grained matrix. So you can see some examples, and actually this top background photo is the field locality for Saturday's field trip, Tiburon Peninsula, just north of San Francisco. And you can see there these very large blocks jutting out of the hillside. You can see here a smaller block, and in this photo you can actually see matrix. So these blocks are surrounded by finer grained material. So you can see that finer grained material often weathers away, and so it will be hard pressed to find that melange matrix at the Tiburon locality. But there are places where one can see the relationships between the block and the matrix, and you can see a lower grade block and matrix on the right. So we've got these sort of, that word melange, it's French. Anybody know what that means? mixture. So, I mean, it very well describes. We get these mixed up materials exposed from subduction zone metamorphic complexes. They'll be mixed up in terms of lithology. So sometimes you find mafic rocks, ultramafic rocks, sedimentary rocks, and in some locations they're mixed up in terms of metamorphic grade. So when we look at the rocks on Saturday, if you're coming, we'll see some eclogites, we'll see some blue schists, we'll see some amphibolites. So we get this mixing process, and there's a lot of evidence that suggests that this is not happening on the exhumation path necessarily, although some aspects of it may involve exhumation, so it's a little bit tricky. But in some cases we see evidence that this is happening at high pressure and temperature. And so just to flesh out this idea a little bit more, this is not even, in some localities it can occur over very large scales. So some places we see very small scale examples of this, but places like the Catalina schist, you can see this mapped area here, and you can see the scale here, a kilometer scale. So we have actually a very large region that has this melange, and you can see these, the mafic blocks are shown here as black blobs, and the matrix are different colors, and then ultramafic blocks, which are larger, are shown in green. So we've got this region, this mappable kilometer scale region that's all melange. And so this suggests that this is not a trivial aspect of these subducting slabs.
Sarah, I'm still trying to wrap my head around the fact that the melange isn't produced by the exhumation.
It may be involved in the exhumation.
But it must happen past prograde metamorphism.
In some cases, that may be the case, but in this example, the matrix, the finer grained materials, have minerals that record the peak temperatures that are identical to or are similar to that of the blocks.
Oh, okay, all right.
So we have evidence, at least from some localities, that the matrix and blocks are cofacial, have the same PT conditions. Other places, that's not the case. The Franciscan has, well, serpentinite doesn't tell you a whole lot, but there's some places where it's clay matrix, right? And you'll find a blue schist facies block in a clay matrix, and there you have a clear difference in grade. And so that may be that's a melange that's partly forming during exhumation.
But the idea would be, if that's not the case, that you basically form the melange and then metamorphose the whole lot?
Yes and no. It's a progressive process, and so yes, to some extent, yes, in some places.
No, thanks.
Yes.
We know if the ultramafic blocks is from the upper plate.
Right, so the question is, do we know if the ultramafic blocks are from the upper plate, right, the mantle wedge, or maybe the bottom of the subducting lithosphere? We don't have evidence. The assumption is that it's from the overlying plate because it's mixing up with materials from the top of the plate, metabasaltic rocks and metasedimentary rocks, but we don't know that for sure. We don't have a smoking gun that will tell us where it's from. Okay, so in these melange zones, we have evidence for physical mixing of materials. And so again, the same locality, the Catalina schist, where we have this evidence that this is happening all at the same pressure temperature conditions. We've got mafic rocks, so we've got aluminum and chromium. And so aluminum and chromium are elements that are thought to be relatively immobile in fluids. So they're used as a reference frame here for trying to tease out processes where you just have a mechanical mixing of materials as opposed to materials that may be transported by fluids. And so what's shown here, aluminum, so you've got mafic rocks, which are the little black circles up here, high aluminum but low chromium. And then you've got ultramafic rocks, which are the black triangles. And the melange matrix are these little plus symbols. So you've got a range of matrix compositions that fall in between the mafic rocks and the ultramafic rocks. So the melange matrix it's essentially interpreted as being a mixture of material that are derived from the mafic blocks and the ultramafic rock. So in this locality, the matrix is being derived, or it looks like it's being derived from the blocks themselves. And their interpretation is that these reaction rinds are forming, bits are flaking off of that, and it's all mixing together, all as it's being metamorphosed during prograde metamorphism. And we see evidence in the reaction rinds also for this kind of mixing. So we've got chromium and nickel shown here at the bottom. The rinds themselves are blue, the melange matrix is the gray, and the green is the mafic blocks themselves. And so we've got matrix over here with high nickel and chromium, blocks with low nickel and chromium, and reaction rinds kind of in between. So we've got some sort of progressive process that we see happening in this setting. That represents, we think, a real physical aspect that happens along with the fluid flow. So it's really difficult to sort of tease out these processes. Okay, I also wanted to mention that in some subduction-related localities, we're talking about rheology and deformation, these phenomenon called pseudotacholites are found. And these are fine-grained to glassy rocks that are found in shear zones. And they form commonly by frictional melting during rapid movement on faults. And so they're interpreted in exhumed subduction-related rocks to be direct evidence for paleo earthquakes. And so you can see a couple examples of them shown here. Right, so I guess, you know, my mental model for what's going on at the subduction interface, I guess in part to answer Adam's question, is that, yeah, we have this process happening. It's happening progressively, at least in some localities, this process of melange formation and the behavior of rocks within the subduction zone. Okay, so in part to help answer that question of Adam's, I'm going to keep talking about melange rheology because I have a few minutes still. The melange matrix in many locations is made of relatively weak minerals. So we get a lot of sheet silicates in these, and that's illustrated on this diagram. Oh, not this one, sorry, a later one. But we get minerals, in some cases, the Franciscan, we have clays. We have a shale matrix, like you can see in this blue schist, surrounding this blue schist block. In other localities, like Syros, we have chlorite and talc. So these are all sheet silicates. These are relatively weak materials. They'll deform more readily than other minerals. And this has led to models of flow of material within melange. And so you can see here an interpretation by Mark Kloos of material flowing. That's what these arrows are meant to represent. The idea is that these blocks are actually moving within this matrix, this relatively weak matrix. And this idea was developed further by Taras Geria and others in 2002 in a numerical model where they model this sort of flow of material, and you can see the greens of the oceanic basaltic crust, the reds of sedimentary material, all mixing within a relatively weak matrix. In this case, it's hydrated mantle wedge matrix. And along with that, they suggest then, you know, this model suggests, if you look at this dot, you can see that there's blocks. The PT paths that are shown down here at the bottom represent blocks that would be found in an outcrop together, but have experienced different prograde PT paths. So you can see here like this purple path versus this blue path. They would all end up in the same place. So I think this model was developed in part to explain this coexistence of rocks, blue schist, eclogite, amphibolite, and so forth, all in one locality. So the question that we're trying to ask is, does melange itself affect rheological behavior, and how does that change with metamorphism? So I kind of alluded to this already, but we have the coexistence in some places of blue schist, amphibolite, and eclogite blocks all together in some places, like Tiburon Peninsula, where some of us are going on Saturday. That's what's shown here. But in other localities, like the Catalina schist, we have these areas, like the amphibolite facies melange in Catalina, where it's all amphibolite facies. We don't see eclogite there, we don't see blue schist there, it's all one facies. So we do have variability in these melange zone rocks. Why is that? And our hypothesis is that actually the melange matrix can change with increasing metamorphism. So in the Catalina schist, we actually get the development of rheologically stiffer minerals like pyroxenes and amphiboles. So you can see here, here's a block in the upper right, hammer, and we can look at melange matrix here that has actinolite. Here's a close-up photo. You can see the nice elongate actinolite crystals. So we get these minerals that behave likely in a more stiff fashion and maybe inhibit the scale of flow. And this maybe is why we have all amphibolite facies blocks in the Catalina schist amphibolite facies rocks. So we're testing this hypothesis by looking at blocks all throughout that map area that I showed you and measuring their temperatures using zirconium and rutile thermometry. So it uses this exchange equilibrium. And essentially, rutile incorporates more zirconium at higher temperatures. As long as we have quartz and zircon present, we can estimate the temperatures of the blocks. So we're looking to see whether there is actually differences in the temperatures recorded by the blocks or not. And is it a coherent pattern? Can we look for temperature gradients across the melange? So we've got a couple of different methods, a lot of different rocks that are found in this melange zone. And it's a lot of data, and I apologize, but essentially each of these vertical columns represents a different sample. First of all, you can see that, you know, not every rutile in a rock records the same temperature, all right? There's a lot of processes like diffusion, growth zoning that actually can act to decrease the amount of zirconium or to have a lower zirconium content in a rutile. So our goal is to look for the peak or maximum zirconium content, but we don't want to take just one analysis because we can also have analytical artifacts, or we could have rutiles that are actually isolated from the reactants involved in the reaction. So we've developed this method whereby we average these sort of top 4 measurements, and that's what's shown by each of these gray bars for each sample. We call it a mean maximum zirconium method. So what you can see is that we get distinguishably resolvably different zirconium contents. You can see the uncertainty of the two methods is shown in the upper right-hand corner. And if you're even, and I am, of course, you should be skeptical of this mean max zirconium method. You can see that we even get resolvably different populations. So this guy here on the left has no overlapping zirconium rutile measurements with this one here on the right. So not only do we think we have resolvably different zirconium contents, but we have samples that have completely non-overlapping rutile populations. So clearly different temperature conditions recorded by some of the blocks in this melange. And here's the temperature conversions. What I showed you before was the zirconium content. So this translates over again into resolvably different temperatures. And here are the different temperatures from the completely non-overlapping rutiles. So we've got temperatures of 646 to 726. There is a melange matrix sample in this. It's over on this part, but it's got, it's got similar temperature range. But we do have a variety of temperatures that are recorded here. All right, so it's not all the same temperature. So why is that? Can we see a temperature gradient across this region? Is there some chaotic movement of blocks in this? So I've got here, this is the amphibolite facies melange outlined in red. All of our samples color-coded for temperature. And we made a contour plot just to make it easier to look at. What we find is that we don't see any systematic temperature gradient with respect to any of the spatial coordinates, including vertical. We don't see any systematic temperature gradient. We have this sort of more chaotic distribution, some areas of high temperature, areas of low temperature, non-systematic. So this suggests that we do have differential movement within this high temperature melange, but that it is happening at a more restricted scale, perhaps, than in other localities. And so this has led us to this little diagram here, which we're still working on. This paper's in review, but this is meant to say that at lower temperature we have sheet silicate. See the little squiggly lines in the matrix? That allows material to perhaps move more freely, have larger scale movement, jumbling up of blocks of different metamorphic grade. Whereas when we get to the amphibolite facies, we get more. These are meant to be our pyroxenes and our amphiboles that are stiffer, that inhibit the movement, so we have smaller scale mobility. But we do have a range of temperature conditions recorded by the block, so we still have evidence for some kind of flow. Okay, I think I'm getting...
Okay, you have like 8 minutes.
Okay, I'm going to just talk a little bit about geochemical cycling, and then I'll open it up to questions. So one other piece of information we can get from exhumed metamorphic rocks is evidence for geochemical cycling. And so folks have looked at element ratios, for example, that people look at in volcanic rocks. So Horst Marschall has looked at some of these melange zone rocks from around the world, compiled the barium to thorium ratio on the y-axis and lanthanum to samarium on the x-axis. The melange rocks are all the little black circles, and he's compared them to arc volcanic rocks, which are the red crosses, and also then done an average of melange rocks here in black and compared it to a spider diagram, compared it to some arcs. And his conclusion is that melange zone rocks are very similar geochemically to arc volcanics, and he has developed this model of these melange diapirs. So he's got this model where you have melange that's actually, because of density differences, is upwelling and forming a diapir and rising and then melting close to the surface. So I don't know if I'm a melange diapir believer, but I think it's kind of an interesting concept anyway. Anyway, the idea basically is comparing the geochemistry of these metamorphic rocks to products or other outputs of subduction zone systems like arc volcanics. And then I think this is the last geochemical cycling slide I have, and that is looking at carbon. So carbon is becoming more and more of interest these days. We're moving beyond just looking at hydrogen in terms of fluids and looking at carbon cycling. And so I wanted to share a study here by AGU and Niculescu, where they looked at, again, subduction melange rocks, looking at dissolution of carbonate. So this is not carbonate reacting with other minerals, it's just pure dissolution. Like the calcium carbonate is just completely dissolving and moving, and you can see that in the rocks and in the chemical changes, and both the calcium and the carbonate are leaving the rocks. And so this, it's facilitated by fluid flow, and this suggests then that this dissolution of carbonate may contribute significantly to cycling of carbon within subduction zones. So I'll just end with the slide that I started out earlier. Hopefully I've given you some insight into the complexity that you get by looking at metamorphic rocks, but there are rewards at the end. So I'll take questions.
Just a reminder, that was the first thing, Sarah. Let's have questions from students and postdocs first.
Sarah? So you answered his question previously, saying that it's still
unresolved, whether the overlying mantle wedge or the slab is contributing peridotite to the melange. But your cartoon, the cartoon you showed from your paper in review doesn't really include much gabbro in.
Right.
And so if you don't see gabbro, would you then assume that it's not even including what's below the gabbro in the slab, or is that not?
You know, that would be one first order reasonable assumption. However, we do see a lot of mixing of materials and jumbling of materials, so I can't 100% exclude it. The general assumption is that it's most likely, I mean, like you said, you don't even see metagabbro, right? So it's most likely the overlying mantle wedge, but I can't like give you a silver bullet and say, oh yeah, 100%, you know? So, yeah.
So the amphibolite blocks that you were looking at where you showed the temperatures, are there any ages on those? And is there any pattern with the ages?
We don't have ages on all of the blocks. There's only one garnet lutetium hafnium age for that part of the, and I'm not sure, well, it's certainly an interesting thing to try to investigate, but I'm not sure if we would be able to distinguish ages at the scale that we would need to, but we don't have them right now, I guess is the short answer.
For the amphibolites you were mentioning from Catalina, did you say, were those block matrix or are those mostly coherent amphibolites?
So the ones for this study?
The ones where you have the zirconium and rutile.
Yeah, so those are blocks.
Blocks.
Yeah,
okay.
Sorry. These are all blocks that are distributed around the amphibolite melange. So.
Okay. I was just going to ask, could you also interpret those range of temperatures as basically progressive crystallization under increasing temperature conditions, as opposed to maybe block matrix mixing?
So I think the idea is that they're different temperatures recording different peak temperature conditions. But that they then have been brought back together. I mean, they each record different peak temperature. I guess I'm not really sure what you're asking.
No, that does answer. And then the other question I had is, what is the matrix material here?
So the matrix material, this is, it's variable. I guess I have the map here somewhere. It's variable, but in some places it's very chlorite rich. In other places it's got the pyroxenes and the amphiboles that I mentioned. So we've got some enstatite, we have some anthophyllite, and we've got actinolite, in addition to chlorite and talc, and it varies a bit in composition throughout the melange.
Okay, thanks.
Other students or postdocs?
Just one question about maybe the terminology or a specific tectonic setting. The accretionary prisms, they are some kind of they're associated with the melange, or all those rocks are in the accretionary prisms? Prism.
Yeah, so I'm sorry, I don't understand the question. Can you say it again?
If the association with the accretionary prisms with melange is the same tectonic setting, or
So I think of accretionary prism as being sediment dominated, and in some cases we see melanges that have sedimentary materials. At the ones that I have studied, there are more mafic and ultramafic materials, so this is not part of the accretionary prism, but some of the, I can't find it. Anyway, the cross-section that I showed you, there are broken, what they call broken formations at the lower temperature in the accretionary prism that to some extent resemble the deeper analogs that we see. So I do think that you can have them in both shallow and deep, if that is answering your question.
Sarah, I was wondering about evidence for deformation within the matrix, and specifically gradients in deformation across the matrix. What sorts of microstructural data you have, or you've thought about looking at?
This is something that we have not investigated. I've thought it would be very interesting to do, but I'm not a microstructure person by nature, so I haven't done it yet. But it's something that I think would be very interesting.
So you talked about how cold subduction zones could be. If you turn around and look at how hot they could be,
yeah.
It's like what? So you talked about there's definitely some amphibolite blocks in some places. Green schist is also not uncommon. Are those mostly retrograde? Is that prograde?
I think in many cases the green schists are retrograde, but I believe most of the cases where amphibolite has been studied, it's prograde. So, and I haven't done a compilation of amphibolites to sort of outline their temperatures. Yeah.
So thinking about the serpentinites again, so we saw a lot of the phase diagrams for what happens in the crust, but there are different types of serpentinites. So I'm not sure if I know this correctly, so it'd be good to get your insight. But if you are generating serpentinization on the incoming plate, would that be lizardite? I mean, I guess, is there a way to tell?
At the base of the lithosphere, I think it would still be a high antigerite. But
yeah, I think it's antigerite, but it also varies because the composition of the lithosphere varies.
I should
so
also
it's
say
compositionally
that
dependent.
These serpentinites, though, the serpentine in these has reacted with meteoric water, and so we can't use those rocks to infer much about the high temperature aspect of their history. So I think much of that is not antigerite even now, but I couldn't use that to infer its history because it's retrograded.
But you can use water rock reaction models to look at what phase you form and then look at natural samples and sort of confirm those. And so there's some studies I can point you to that, but there is some variation. It's not all one phase of serpentine.
How many of you seen this diagram before? Okay, awesome. So I'm going to spend a lot of time on it. This is a metamorphic facies diagram, okay? And this is based actually originally on field observations of metamorphosed mafic rocks, okay? And so all of the different names in these different fields, so temperature on the x-axis, pressure on the y-axis, these are the names of the metamorphic facies. And they were based on mineral assemblages. So not just a single mineral, but a grouping of minerals that were found in a rock. Right? And the facies, they recognized that different mineral assemblages represented different pressure temperature conditions, and over the years people have started assigning temperatures and pressure conditions to this diagram. What is also on here, in addition to the various facies names, are these arrows. And the arrows represent pressure temperature paths. Okay? And so we can imagine a rock at the Earth's surface, actually off to the left here on the diagram, encountering a variety of tectonic environments and following different paths on this pressure temperature diagram depending on the tectonic environment it experiences. So if you have contact metamorphism or a mid-ocean ridge metamorphism where you actually don't have a lot of pressure but you have a lot of heat in the system, it will follow a path like this bottom arrow, low pressured over temperature environment. If you have continental collision, you get what's called regional metamorphism, and you follow this intermediate P over T line. And you get rocks from zeolite to prehnite pompelia to green schist facies to amphibolite facies to granulite facies. Those are the names of the facies that the rocks experience. Subduction zones are what we're interested in, and they follow this high P over T line for subduction zone metamorphism, okay, because we're increasing the pressure before the temperature has a chance to catch up with it. And so we encounter zeolite, prehnite pompeliite, but then in most cases we experience blue schist, boy, I can't talk, blue schist and then eclogite facies. I'll be returning to this diagram a few times just to provide a reference frame for this talk. Okay, so a little bit more detail on how these PT conditions are determined. Again, it's this assumption of chemical equilibrium, and there's sort of two basic approaches to this. One of the approaches is classic thermobarometry, all right? And this is based on minimizing the Gibbs free energy of a chemical reaction among minerals, right? So as a petrologist, we look for minerals in a rock. So if we have a rock, for example, that contains garnet, and kyanite, and quartz, and anorthite, we can write a chemical reaction among those minerals, right? And we then I hope everybody got a good shot of caffeine to hear the rest of the talks this morning. I was pleased to hear from Torsten's talk this morning that geology has a relevance to geodynamics because that's what I care about. I'm a geologist. I study metamorphic rocks exhumed from subduction interfaces. So what I'm going to be talking about today is what we can learn about subduction zones by looking at rocks, the metamorphic rocks that are exhumed from the subduction interface. And one of the take-home messages is that subduction zones are very complicated. What we see, the evidence that we see from rocks that are exhumed from subduction zones is that there's a lot of complexity, but we can also learn a lot about the processes that occur within active subduction zones by looking at the rocks that have been exhumed from fossil subduction zones. So I have here, the stereotypical cross-section of a subduction zone. And of course, rocks are exhumed from lots of different parts of subduction zones. I for my research, I focus on rocks that are exhumed from the subducted slab. So my talk is going to focus sort of mostly on subducted slab, relatively deep rocks, a little bit of the shallower part of the system as well. And these rocks tell us about a lot of different things. They tell us about the materials that exist within subduction zones. So it's our only direct sampling of these materials that have been, at that subduction interface. So we get information about the mineralogy and the properties of those materials, the conditions, pressures, temperatures, fluids, so forth that are experienced within subduction zones, and then the processes that happen within those subduction zones. And they provide complementary information to observations from active subduction systems. And so this is a diagram of the so-called subduction factory from Tatsumi in 2005. And this is one way to look at a subduction zone, which is you have input material, oceanic input, oceanic crust, sediments in the brown on the top. And then you have outputs, various outputs. You have arc volcanoes, so some people interrogate subduction zones by looking at arc volcanoes. You have earthquakes, another output from a subduction zone, so you can investigate earthquakes, mantle, residue material, and so forth. But what I study is what goes on inside of this subduction factory, right? So all of these inputs go into the subduction zone, into the subduction factory. We can interrogate and hopefully help you out in identifying and characterizing the rocks in the field. So that's my talk has kind of two purposes. One, to talk about this information, and one, to introduce you to the rocks themselves. Okay, so to introduce you to the rocks themselves, we'll talk a little bit about the thermal structure of subduction zones. Christy touched a little bit on things that we call thermobarometry. This is based in equilibrium thermodynamics. And so this is how we estimate pressure temperature conditions from rocks that are exhumed from metamorphic, from the subducting slab. We use equilibrium thermodynamics, all right? And this is based on the fact that systems, chemical systems, tend to minimize this quantity called Gibbs free energy, right? This is a chemical potential energy. And a lot of times in teaching about this, we use this kind of diagram, and the analogy is made to gravitational potential energy, right? So in gravitational potential energy, systems tend to minimize that potential energy, right? If I have a ball here and I let loose of it, it will fall to minimize that gravitational potential energy. So we have a similar kind of concept here with this Gibbs free energy, where high Gibbs free energy is up, and low Gibbs free energy is down, and the system will act to minimize the Gibbs free energy of the minerals that are of the rock, the minerals that are present. And so what's shown here, you can see there's some topography to it. It's not just up and down, right? Is carbon. And so carbon at Earth's surface, the stable form of carbon is graphite. Okay, so we see here stable graphite. That's the minimum Gibbs free energy configuration for carbon on the Earth's surface. Right? We also, however, have diamonds. I have an engagement ring that has a diamond, and it's not turning to graphite anytime soon. Okay? We call this metastable. All right? So it actually has a higher Gibbs free energy, but it's got this little activation energy. That's what this E sub A is meant to indicate on here, that it has to overcome in order to convert to graphite. Okay? And so this reaction takes place at a very sluggish rate because of this activation energy. And so we have diamond that's stable at the Earth's surface, even though we have diamond at the Earth's surface, even though it's not stable. Okay, but generally speaking, systems act to minimize Gibbs free energy, and that's the basis for all of the estimates of pressure and temperature that you will see in the literature based on mineral assemblages, mineral compositions, and so forth. Okay, if this assumption of chemical equilibrium holds, we can determine what the pressure and temperature conditions are for this assemblage to be stable. And it will depend on the chemical composition of these minerals. And so what you can see on this pressure temperature diagram are a bunch of yellow lines. And each of those yellow lines has a different K value. That's an equilibrium constant. Right? That's determined by the composition of these minerals. Some of these minerals, quartz, that's generally pretty pure quartz. But other minerals like garnet can have impurities, can have different components in it, almandine, spessartine, pyrope, and grossular, which is shown here. And so these K values will vary depending on the compositions of the minerals. So you measure the compositions of the minerals, and that tells you that your rock was in equilibrium along, let's say your equilibrium constant is 0.1. Then it defines a line here of pressure temperature conditions for your rock. That's one way that is used to determine pressure temperature conditions. And then ideally, you have another reaction that is a line that's more vertical. One is referred to as a barometer because it's relatively horizontal. If you can get a thermometer equilibrium assemblage, that provides a vertical line. You can have two lines that cross. It allows you to determine P and T with some precision. Another method is referred to as pseudosections, or some people call them mineral assemblage diagrams, or MADs. And in this, again, it's using that same basic premise of minimizing the Gibbs free energy of a system. But here, essentially, the bulk rock composition is input into a large thermodynamic database. And the database, there's a lot of them. You may have heard of Perplex. You may have heard of Thermocalc, Theriac Domino. There's a whole bunch of these that people use and calculate the mineral assemblages that are present for a given bulk rock composition. All right? And so then what that produces, and I think Christy showed this in her talk too, is a diagram like this that shows the minerals that are stable, the mineral assemblages that are stable at different pressure temperature regions within this diagram. And then it also can produce things like mineral compositions, because many of these are minerals that are solid solutions, so they have a variation in composition and so forth. So caveats, there's a lot of concerns. One has to approach these methods carefully, right? Equilibrium thermodynamics tells us about the minerals that are stable at a given pressure and temperature, but it doesn't tell us about how quickly the system might reach equilibrium. My diamond, for example, that's not very fast, right? If I were to have a variety of outputs, but really what I want to know is what's going on inside the subduction factory. And this is a diagram from a paper that I co-wrote with Gray Bebout. And essentially, I want you to contrast this with the diagram that I showed earlier, and that is that this subduction interface, what we see from the rock record, the subduction interface itself is really a lot more complex than we draw in our simplified two-dimensional diagrams of subduction. And so we spent a lot of time reviewing the literature and looking at different features that are found in exhumed metamorphic rocks. And you can see that we sort of tried to encompass all of what is found in metamorphic rocks in this diagram. Now, this is not representative, perhaps, of a single subduction zone, and there's probably some issues of scale in here, but it tries to encompass a lot of the different processes, like fluid flow. You see the blue arrows, mixing of materials. You see the different colors representing different rock types getting mixed at the interface. Of course, deformation, faulting, and so forth, veining, fracturing. All of these processes create a very complicated interface between the subducting slab and the overlying mantle wedge. So my talk is broken into 4 parts, 4 different types of information that we can get from metamorphic rocks. The first part is thermal structure, where we can learn about pressure temperature conditions from exhumed metamorphic rocks. The second has to do with fluids. Metamorphism generates fluids. What evidence do we see in the rocks exhumed from subduction zones for those fluids? Rheology and deformation. What kinds of histories do the rocks record about the behavior of the material within the subduction interface? And finally, geochemical cycling. So part of this is just to give you some sense of the types of information that we get from the exhumed metamorphic rocks. But I'm also tasked a little bit with telling you a little bit about those rocks themselves. We're having a tutorial this afternoon where you're going to be looking at rocks, and some of the rocks you're going to be looking at are metamorphic rocks. And I know that we have people with a variety of backgrounds in the audience who may not be as familiar with the minerals and rock types that are exhumed from subduction zones. So part of what I'm going to do also is to tell you a little bit about the names of the rocks and the types of minerals that we find in those rocks, so that for the tutorial this afternoon, you're able to hopefully better identify those minerals and give those rocks names. And then also, if you're going on the field trip with us on Saturday, we will again be looking at exhumed rocks from the Franciscan complex, and so that will